Hello.
Oh, hello. Hello. I warmly welcome all of you for the astronomy webinar.
Yeah, hi guys.
So, so I would like to welcome our speaker, Dr. Prasanna Deshapriya. So, before starting, I will give a brief introduction about Dr. Prasanna. Uh, he's a he's a graduate of Faculty of Science, University of Colombo, Sri Lanka, and he did his masters in Vietnam, and he did his PhD in Paris Observatory. Currently, he is doing his postdoctoral research at the Paris Observatory, and his field of research is near Earth objects. So I think uh, I was waiting until all the participants come. Now I think we have the correct atmosphere to initiate the speech. I would like to hand over the session from now on to Dr. Deshapriya to make his speech. Over to you.
Yeah, thanks a lot, Shubhat, for the introduction. Yeah, so let's get started. I'm sorry for the delay. I had some connection problems. So let me see if I can share the screen. Okay, are you guys able to see my screen?
Yeah, we can see it.
Okay, so yeah, so let's start. Yeah, so thanks again for inviting me to talk about the results of the OSIRIS-Rex mission, which I'm a part of. So I would like to share some of the information we got from the very initial phase of the mission, and then give you some ideas about what the mission is about and why it is important to study asteroids, and especially those which are near to the Earth. So yeah, let's get started. We'll do the next slide. Okay, so OSIRIS-Rex itself, the name comes from a lot of combination of different aspects, which is addressed by the mission. So it attempts to probe our origins being the appearance of life on the Earth. We all know the life started at some point on the Earth, and so it's a very ongoing question in terms of astrobiology and current research that how and what triggered the appearance of life. So people think it's the arrival of the organic compounds that permitted the creation of more complex reactions that ended up being what came to be as life. So this bringing by samples from an asteroid, because these asteroids are basically, I remind you that are the building blocks of the solar system, from the material from which the planets formed, and also the sun. So studying these parts, it's more like because on the Earth and the other planets, you have this material that's undergone a lot of changes over the years due to geological activity and a lot of other processes that have changed the way the material appeared in the beginning. So it's like you look at a cake and like for the first time and try to find out from which material the cake was made. So we know it's made from rough ingredients, and it went to a heating process. So it's baked, and like you have the cake right now. But if you really wanna like know what happened, you have to go to the kitchen and like found where it was made and find the ingredients. So it's in some sense it's like this. So we have to get an understanding of the beginning of the solar system. We have to go to the objects that remain from this process. So these are the stuff that remains still from the planetary nebula from which the planets form in the solar system. Also, we have also comets on the other hand as a counterpart of these forces. So these small bodies, asteroids and comets are the material in the solar system that have a lot of relation to the origins and that have stayed unaltered, as to speak, to a least amount. So that is why we are going and trying to bring a sample from an asteroid before to the Earth. So this is to address this question of origins. And also we focus this mission on the spectral investigation. So this is the spectroscopy aspect. So we know that from ground-based instrumentation and telescopes in orbit, we can get some idea and some information about the objects that are in space, so asteroids, let's say. And how really they compare these observations when we really go to the site, go close to the objects and try to look at them, how this appears. So this is to improve, because these kind of observations near in situ observations near the asteroid would help us to better understand what our observations from the ground and the space are really telling us. And even the sample that are brought back to the Earth from these asteroids will tell you more information about how to improve your techniques and what are the things you need to improve. And also there's a part of resource identification. So this is for future space-faring population and civilization aspect. So this is to, let's say, to help extract minerals that are important to create important products like water and oxygen for interplanetary travels in the future, which is, I think, really important. So this also, by analyzing an asteroid and identifying what amount of material is present, and if, because water is there, it's connected to some other minerals, so it's not in the form liquid, but you can, if you know it is there, you can extract it. Also, there's this current boom of space mining, and there are a lot of companies that started out on space mining to mine for like rare metals and very valuable things that are least present on the Earth. Yeah, so this also tries to address the question by an in situ study of an object in the near space area. And then we have this aspect of security. So this security being the planetary defense, as you say, we all know that dinosaurs disappeared from the planet Earth about 66 million years ago. That was an aftermath of an impact with an asteroid or a comet. So this could have, the opportunities are of course rare, but this is, you cannot neglect it. And there are a lot of things that come into play, like the different forces that change the orbits, because there are a lot of asteroids that are in main belt, get ejected from the main belt and sometimes go away from the solar system, or like come near to the inner solar system, where they become Earth crossers or Mars crossers, and then eventually a lot of forces like Yarkovsky force could even change the orbits unpredictably and have an impact on your body. So this is to understand these forces that really act upon the changing of orbits of small bodies to prevent any potential asteroid impacts. So this asteroid Bennu itself, it's very small asteroid, about 500 meters in diameter, and it's the right type of object to go and bring samples to address all these questions. So that's why it was chosen as the target of the space mission. So here you can see some images of the Bennu. To the right, most image shows how it looks like. And the spacecraft OSIRIS-Rex was launched in 2016. And we arrived at the asteroid in almost 2 years ago, let's say. It's December 2018. And since then, we've been working to find sampling sites, to find samples, and then bring that to the Earth, these samples in 2023. Yeah, so this is quite a short introduction, and let's talk a bit more about the asteroid itself. So this is a retrograde rotator, so its orbit is in, so it rotates in opposite direction to its orbit around the sun. So it has we could say it's an inclination about more than 180 degrees. So this sort of objects sometimes have this spinning top shape because of the centrifugal force is very important. These objects, a lot of materials are found near their equator. So this sort of forms sort of a bulge, as to say. And it takes about 4 hours for one rotation, and it has a density which is a bit over than that of water. So these are actually very porous objects. These sort of objects form from collisions in the main asteroid belt, and then these collisions lead to reaccumulation of different bodies. So this is why we call these bodies the rubble piles. So these are very light and very porous objects. And it has an albedo about 4%. So the albedo, I don't know if you are very familiar with this term. So this gives an idea of what the reflectivity of a surface. So let's say snow, for example, has an albedo about 100%, close to 100%. And this is an object which is even darker than coal. So this is a very dark object because these have a lot of organic compounds. They do not reflect away a lot of light that is absorbed, that arrives at the surface. Yeah, spectrally speaking, this is a B-type asteroid. So this means it has a blue spectrum. So in the asteroids taxonomy, in spectroscopy, we have this red and blue spectra. So red means that when you with the increasing wavelengths, your reflectance increases, whereas the blue spectrum means your reflectance decreases with the increasing wavelength. Yeah, so yeah, its orbit is a bit inclined, but also not too much, and it's few degrees from the ecliptic. Yeah, so the mission is as I said earlier, to bring back samples from the this asteroid to the Earth. So there are different phases of the mission where we have different targets. So as I said, we arrived in the asteroid this time, and then we have to collect the samples, for example, this year. So sample collection is scheduled in August later this year, so in about a couple of months. And then we have a return window, so you could come back, we could start the return to the Earth as early as March next year, 2021, or even we could stay even longer, about 2022, and even come back, because there are a lot of uncertainties that go into the mission, because if the samples, these are not some things that done before, so these are very unprecedented processes and science experiments, so we leave a lot of time for these uncertainties. So even like we did not succeed in getting enough samples in the first attempt, we could attempt more times to get samples that are needed. So that's why we have even longer times to stay at the asteroid. So we could come back to the Earth in whatever the time we depart. If we depart before the middle of 2022, we could come back to the Earth still at late 2023. This is the timeline, and these are this side I would not go too much into detail because it is very mission specific, and it gives different types of orbits and different observation campaigns that are done to address different questions. So this also depends on the different angles we want to get using spectroscopy data and imaging data to build better shape models. And so shape model is a 3D rendering of the object, so which helps us to navigate around it and make some observations. So the observations are planned using a shape model. So it's like a point cloud, if you want to imagine, or a 3D source. So you need the images to feed into, and also like a laser arranging data, for example, to make this. And so we do some rehearsals in the mission, and then we go for the touch and go, which is the sample acquisition. So this is just some ideas about the mission. Yeah, so now I'm getting to the payload of the mission. So this is payload being the instruments that are inside the spacecraft. So here you see one plane of the spacecraft. normally all these science equipments are stuck in one plane. So because you need to use it, because you need to observe using different instruments at the same time. So it makes more sense to have this like this way. So you have this big antenna which is deployed after it was launched. So you can see its number G is given this indication in letter G. So this is the antenna that's deployed. So this helps the communication with the Earth, of course. And we have 3 spectrometers. So OSIRIS is one of them, which operates from about 0.4 microns to 4 microns. So these to characterize the visible spectra and infrared spectra of the Bennu. And we also have a thermal emission spectrometer. So this starts from about 5 microns up to 100 microns. So this is to study the material in using mid-infrared domain, and also to understand how these thermal to address the properties like thermal inertia, and to get better understanding of the material that is from different silicates or different kind of rocks that are present on the surface. Also, we have a regolith X-ray imaging spectrometer. So this this is to identify different elemental abundances on the surface. And also we have a suite of cameras made of 3 cameras. One for observe very localized areas with a high spatial resolution, and one with a lower spatial resolution but with 4 filters. So this gives you better spatial resolution than the spectrometer of OSIRIS, for example, but still get more an idea of the spectra using spectrophotometry using the 4 filters that are present on this camera. And also we have a small camera to observe the sample acquisition during the touchdown to see what happens and how this regolith on the surface, because these are like very powder-like material. There's very less gravity in this asteroid, so this is very interesting experiment to observe what happens when you like touch down on an object that is very porous and very less dense and covered by material that is regolith. We say regolith that is being very dusty like material that is present on the surface of the asteroids. Yeah, so this is the, and also we have a laser altimeter, so it helps even make DTMs, so digital terrain models. These are very important to assess hazards in an area. When you want to come down and observe these DTMs, means these are like still shape models, so these are very localized ones. Gives an idea of the terrains and also helps us to understand the topology of the surface. So this is done using laser. Yeah, so this is the payload of the science instruments. Yeah, this is some slides about the cameras. I will skip this and go forward. So these are all again these instruments that how they work, and also we have a an instrument called Rexes. Yeah, it's as I told earlier, so it observes again the minerals, the elements that are present on the surface, and especially this is important because this is a student instrument. This instrument was built at MIT by students and through many generations, of course, and then it was integrated successfully to the spacecraft, and they've obtained very interesting results so far using this instrument. And here is how we do the sampling. So here you have this image of the sampling head. So this like circular object on this image on the left is the sampling head. So it has a diameter about 30 centimeters. So it touches down on the surface, as you can see here on this is a simulation that was done on the Earth, of course. and then we have some nitrogen gas coming on the sides to give some inertia to the objects, the regolith that are present on the surface, and then using the mechanism that is in the image on the right, we can try to absorb the material to this sort of, it's like a vacuum, so you can store the material, and we plan to bring back about 60 grams of material to the Earth. And that so far there have been space missions like Hayabusa space mission that went to the asteroid Itokawa several years back, and it brought about less than 1 gram, I think, of samples. So this will be the, and also we have this Hayabusa 2 space mission that is still ongoing. So this is another space mission to a near asteroid called Ryugu, from which they successfully acquired 2 different samples. And they are bringing it, nowadays on route to the Earth, and they will come to the Earth later this year. So this 60 grams would be the largest that would be acquired from an asteroid so far. Yeah, moving on. So we arrived at the asteroid, and when you arrive at an object, normally in a space mission like this, it is very important to find if there are any other objects that orbit this asteroid. For example, if it has any satellites. So it's very important for the safety of the spacecraft, because in case of satellites, very small ones, like even if it's the size of a few meters or even several centimeters, it could have an impact on the security of the spacecraft. So first we look at once we were in the Hill sphere of the asteroid. So this is the area where the objects could be. Hill sphere is the object, the sphere of influence of a body where an object could be in orbit around it. So it's, for Bennu, it's about a little bit more than 30 kilometers. So as we got close into the object, we were looking for any satellites or even any dust plumes. So these are sort of activity sources. Sometimes you have some bombardments from meteorites, and that would reveal volatile material that would lead to some dust being ejected from surface, and we were interested to monitor any activity like that. So we did not find any such particles. So that was we could successfully arrive and get in orbit around the asteroid. So here what you're seeing is 3 different views of the asteroid. Let's say one on the leftmost one is the radar image that we had from radar observations of Bennu. So this is before the arrival of the mission, because we need to have a shape model to do the mission plannings. So using this radar, so you send some radar signals, and from its feedback you are able to make a shape model of the object. Of course, you have to have the asteroid very close to the Earth to do this. So because Bennu has a synoptic period about 6 years, so it means it comes to Earth close by, more or less, in about 6 years. So we could, over the years before the mission, we could build up a shape model using this radar observation. So this radar shape model is on the middle image, and to the right you are seeing a real image of Bennu as you arrived, like we saw. So you can see how accurate this model was, and we were very good. The mission was very good in determining the shape, which was very helpful for the first phase of the mission and for the mission plannings. And here is a more detailed resolved image showing full rotation of Bennu. So as you can see here, I remind you its diameter is about 500 meters. And you are seeing a lot of structures with a lot of different albedos, so different reflectivity, let's say. Some dark areas, some rocks, and So the object being to bring a sample from this asteroid, it looked a bit less convincing because there seem to be a lot of boulders that appear. On the limb, you can see the limb is the area that is with the darker side of the asteroid. So whenever it rotates, if you look at this area to the right, you are able to see the structures of the surface. For example, you have this big rock. Let's see if it rotates, and even some craters. And so this also depends on the angles and weaving geometry to understand. If you look at the head-on an object, it's very difficult to understand its morphology. But when it's at the edge, because you're at the phase angle is different. So this is the angle between this illumination and the observer. So it's different on these different areas of the surface. So you can easily make out the surfaces on the edges. So here is one shot of this from this image. So this image has a spatial resolution about 33 centimeters per pixel. And I remind you that the sampling device has about 30 centimeters per as its diameter. So literally we are going to sample 1 pixel from this image. So yeah, this is an image taken at about phase angle 48. So if you're not familiar with these phase angles, again, I repeat, it's the angle between the observer and the illumination source, which is the sun in this case. So different elements on the surface has different phase angles, and it allows you to see different geological features that are present on the surface. So here are two being rocks that are present on the surface, as you can see in these red boxes. So these are, we think, probably from some impactors, or even from the progenitor of the Bennu. So as I told you earlier, Bennu is a rubble, accumulated rubble pile. So this is come from a very disruptive impact between asteroids in main belt many years ago, thousands, millions of years ago. And then because of the gravity regime, it allows itself to accumulate. So it's organizes itself in a different physiologically different way, but still it's the same body. With also, of course, the contamination from the impactor. So we think these big rocks are from the impactor itself, or the Bennu's progenitor. So the object from which Bennu, the main object, let's say sort of a planetary embryo, sort of an object from which Bennu got created. And here you have sort of a projection on a map of Bennu and how it can be seen. So we defined a 0 longitude, and then for the moving on of the mission to make it easier to compare the results and communication, which we've made this sort of, you have to first, when you arrive an object, you have to define what the 0th, for example, you have on Earth the greenish line with 0th longitude. So like this, you have to define an area for the easiness as a standard. So here's the maps. You can see still these big boulders that are present, and also near the equator, you can maybe identify some structures like craters. And because of the shadows, if you look at this top 4 images of Bennu, you can see different shadowing areas, which again gives the understanding of different morphological units that are present on the surface. And here are 2 images of more or less the same area on the asteroid. So they were taken about 70 minutes apart from each other. And what you can see here is the importance of the phase angle, as I told you earlier. This is a crater on the left image where, if you can see my mouse hovering here, it's a crater, but it's very difficult to identify it using this observation geometry. But when you are at this other geometry to the right image, you can see the shadow of it, and so it's very clear that it's a crater. of this shadow. So all depends on weaving geometry, in fact. And here is the largest rock on Bennu, which has about 58 meters in its largest dimension. And this was also a feature that was resolved in the original shape model using radar data. And this is again the same object. Here you can see its height, which is about 22 meters. So this is an image taken at a different angle, of course. And again, some geological features that are present on Bennu. Yeah, so now I would get in towards major spectroscopic results. So these results come from the OSIRIS spectrometer. So on this circle on the left, you are seeing the field of view of the instrument. So the signal, so we have the Bennu inside it, and also it has a signal coming from space. So we've taken the spectral signal of this field of view and used about about 34 such spectra to build the mean spectrum of Bennu at the arrival. So what you are seeing here, in black color on this plot is the spectrum of Bennu from in the near infrared area. So what is the most distinctive feature is this absorption band at around 2.7 microns. So you see a drop of reflectance, so it's a normalized reflectance. And this is an absorption band due to the presence of phyllosilicates, hydrated phyllosilicates. So this is the layers of silicate material that is present on Bennu. This indicates that Bennu has been altered aqueously. So it means that Bennu has undergone aqueous alteration. It means water was present at some point in Bennu's life, and it was heated. And during this heating process, the water probably, of course, it was during its cold environment, was present as ice in the first place, we think. And then when it was heated up, it became water or liquid water, and it got sublimated away. And some of them chemically reacted with the silicates that were present on the surface, and then became embedded in this in Bennu, leading to this. So heating source could be an impactor, or even it could be some radio or isotopes. So this could be some short-lived aluminium or iron radioisotopes that would have as they decay with the half-life, so they would emit radiation, and this radiation would give the heat, pretty much like activity of a geologic body. So, and what we did was actually to compare it with the meteorites. Meteorites are the best examples of the asteroids because they are naturally delivered to the Earth. And so if you are able to find meteorites and compare their spectra, you can try to get an idea. So we have like several meteorites. These are called carbonic chondrites. So these are the material that have like conroots. I don't know if you're very familiar with this terminology. So these are these spherules that were formed initially in the solar system, and then they got embedded into the material that was abundant, and then they got implanted on the asteroids as they accumulated more and more matter, and then as they come to Earth, you can still see these chondrites. So and the composition is mainly from organic, so it's carbonic, and so we have some analogies. So we think the CM1 and CM2 meteorites could be more analogous to Bennu and what we see there. So this was not something that we discovered from the Earth, but at the arrival of the asteroid, then was one of the biggest findings so far. And what we found also was the Bennu's speeding actually in its rotation. so Bennu are, because we had observations from 2000, from um, 99 up to the arrival of the Bennu. So because of the Earth's synodic period being 6 years, every 6 years it got closer to the Earth, and we could measure it in 6 years consecutively, and we see an increase of rotation rate of the Bennu. So this is attributed to the York effect, which is okay. This effect arises from the fact that Bennu being a non-spherical body, and it's constantly hit by photons from the sun, so which makes them heat up the surface. And then when it radiates this material as infrared radiation, it exerts a force, a recoil force on the surface. Of course, instantaneously, it is a very negligible force, but the force does not cancel out as it's not spherical. And over the course of thousands and millions of years, this force could accumulate and lead to increase of its rotation, or even it could even change and bring it back to the to the Earth, bring it back to bring it close to the sun, because it loses its orbital energy, and also even it could go away from sun. So its image axis could decay or increase depending on how it rotates. So this one is called Yarkovsky effect, but the one I'm talking is this called York effect, which is very important for dynamics of small bodies. And we observed this in satellites on around Earth. So these are, of course, artificial satellites. And we've observed over the time that because due to the same effects, their rotation rate is increasing. And so this